Good day, everyone. The focus today will actually be on Bayesian inference, and of course, uh, I'm actually going to be walking you through the difference between the likelihood inference and Bayesian inference. And the application of Bayesian inference, and generally the statistical architecture of Bayesian inference. Of course, I'm actually going to walk you through that in today's lecture. So, like I said, that's going to be our focus today. Okay, so in the outline, I'm actually going to have a review of what we call beta binomial posterior density. I'm going to have a kind of derivation of the Poisson and gamma posterior, overview of Bayesian inference and computation, the conjugate priors, illustrative examples, Bayesian confidence interval, and so on like that. So that is going to be the focus today. Of course, it's actually loaded. We're loaded today. Okay, so I'm actually going to achieve this one by one. Okay, so I'm actually going to start by having a review on beta binomial posterior density. Okay, I'm going to have a review on that. Okay, I'm also going to have a derivation of Poisson gamma posterior density, overview of Bayesian methods. Okay, so let me first start with the overview of Bayesian method. Bayesian methods have been widely applied in so many areas like medicine, ecology, environmental sciences, finance, political science, and so on like that. Okay, and of course, the idea behind Bayesian, it was actually introduced by Reverend Thomas Bay, 1759. In 17th, Reverend Thomas Bay is actually believe that in addition to data, okay, like for instance, if you're trying to understand the environment we live in, maybe we want to understand our political environment, we want to understand our medical environment, we want to understand the economic environment, we want to understand it, and so on like that, of course, if we want to understand our environment, we actually need to collect data. So the data will actually comes in terms of a form of likelihood. But Reverend Thomas Bayes believe that if we can actually incorporate the prior knowledge with the likelihood, that we are actually going to have a way to improve on, on the quality of our model. If we do that, so so he actually suggested that in addition to the likelihood, we should also consider the prior probability. What do we mean by prior information? What do we mean by prior probability? The prior probability is just the probability of the state of nature before data are collected, because they actually believe that we have certain thing in mind in terms of experience and so on like that. That the moment we actually combine, that with the likelihood, of course, we're actually going to have what we call posterior. Okay, and the posterior is actually going to be better than just using the likelihood. Though there have been some argument from the frequentist point of view that before the likelihood can actually be improved upon, that depends on whether you are using a very good available information or not, okay, which we call prior. Okay, and some of them has actually, they've argued the sensitivity of priors, believing that when you have a different kind of prior information, which some of them believe that is more or less a belief, that different people could have different belief And of course, different belief will lead to different posterior, because since the data is assumed to remain the same, and what we actually we actually want to allow the parameters to vary. Of course, in that situation, they believe that different probabilistic expression of our belief, our prior belief, will actually lead to different posterior. That is the argument. Okay. But on the other hand, the Bayesian actually also argue that, of course, there are ways to actually select the best prior that can actually give, you know, a very good posterior. Okay, so I'm actually going to be walking you stuff like this. Okay, now in the overview of Bayesian method, the Bayesian approach provides a formal framework for propagating uncertainty. Okay, we live in a world of uncertainty, because of the fact that there's a variation in the world, and where different things happens in different days, and that is why we're actually curious about what is going to happen next. And as a result of that, uh, the Bayesian approach is actually designed, to provide a formal framework to propagate uncertainty. Okay, and because of that, it's actually well suited to building complex model, by linking together multiple submodels. Okay, so you have different kind of models that you can actually uh, combine together, and to be able to understand uh, the complex situations. Okay, that is characterized by an uncertainty or stochastic environment. Okay, so we can obtain estimate and uncertain interval for any parameter, because under the Bayesian point of view, the belief is that the parameter is actually going to vary. Okay, and if parameter vary, of course we can have a way to estimate that. And not only that, we can also have, of course, when we are talking about estimation, uh, we're going to talk about the point estimation and the interval estimation, and we're also going to have a way to test hypotheses about the value of a parameter. Okay, so the Bayesian inference doesn't rely on asymptotics. What do we mean by asymptotics? Of course, in the likelihood, okay, the likelihood, there's what we call the law of large numbers. Okay, before you can actually get something that makes sense, like, um, you know, uh, we normally assume that you got to take a very large sample size. I'm actually talking about from the likelihood point of view. Okay, I'm referring to the frequencies approach that make use of likelihood inference. Of course, their inference, the likelihood inference actually rely on asymptotics. Okay, and when I talk about asymptotics, I'm talking about the large sample theory. Okay, the fact that the sample size should be sufficiently large, or before we can actually have what we call a normally distributed kind of situation, upon which statistical inference, we have have a kind of foundation. Okay, and of course that is the foundation of the statistical inference, whether you want to estimate hypothesis, or you want to test you want to estimate parameter, or you want to test hypothesis. Okay, but you know what, the Bayesian inference doesn't rely on asymptotics or analytical approximations. Okay, so if that is the case, then we're actually going to move right now. Uh, since we're talking about the idea behind the Bayes inference is just that we actually are going to combine, the prior knowledge with the likelihood. Okay, that's exactly what we actually, the idea behind Bayesian inference. But like I said the other time, um, the frequencies actually argue that how that you know because of the fact that some priors could be weak, the fact that some priors could do could be bad, could actually lead to a very bad posterior. Okay, and that is the reason why we actually need to understand different kind of priors that we have on ground. Okay, so that we'll be able to know the one that can actually give us a very robust and efficient posterior. Okay, now there's something I actually want to talk about right now. There are different kind of prior, but I'm actually want to talk about weak prior. Now, let me tell you this. In general, if I want to talk about prior information, it's just the probability of the state of nature before we collect data at all. Okay, the probability of state of nature before we collect data at all. That is what we call, and of course, we could have a weak prior. And what do we mean by weak prior? The weak prior is more or less like a non-informative prior. Okay, it's just being used as a point of reference, and at times we call that ignorance. The kind of ignorance of prior. Okay, and why do we use that at times? If we actually accept, the subjective nature of Bayesian statistics, okay, and probably maybe we're not comfortable using subjective prior, okay, therefore we can actually specify, uh, a weak prior. Okay, specify the weak prior represent no prior information at all, but that is actually going to serve as kind of reference. Okay, like I said, it's actually going to be not informative. Okay, so the idea is just to have a completely flat prior distribution, over all possible values of the parameter. Okay, that is the essence. And unfortunately, this could lead to an improper distribution being used because uh, you know some weak priors, of course, they could invalidate the a very good probability distribution. And of course, I'm actually going to showcase that. Okay, you're going to see that in the as time goes on. Now, in tossing of a coin, okay, of course, we know in a coin, we have two sides in the coin. So that X shows up, or the head shows, or the tail shows up. Okay, so when I have a beta, okay, of course, because of that, I'm actually going to be focusing on the proportion of probably the number of time a particular characteristics of interest shows up. Okay, and if I want to do that, of course, the probability distribution that we're actually going to use for that is going to be a beta distribution of the first kind. I believe you guys remember the beta distribution of the first kind, which is f of x equal x raised to power alpha minus 1, 1 minus x raised to power beta minus 1, divided by b alpha beta. Okay, you remember that? Where alpha is greater than 0, beta is greater than 0, and alpha, and of course, you know, our x, which is actually it's going to be a proportion because it's going to lie between 0 and 1. Okay, that's what we call a beta distribution of the first kind, because there are two kinds of beta distribution. We also have the beta distribution of the second kind. But what I'm trying to talk about right now, we're focusing on the beta distribution of the first kind because if you look at the range of the characteristics of interest, the random variable right here actually lie between 0 and 1. And that is, we use a beta distribution to model proportion, okay? And that is the reason why it's actually coming up in the case of tossing a coin. Because in tossing a coin, because we have a certain event in mind, okay? It could be the event of the number of heads that shows up. Okay, so In a situation where we are looking for prior, okay, like I said, uh, since if I have a coin, if I'm choosing a coin, of course, if I investigate the number of probably the head that is going to show up, of course I know that is going to be a binomial process. It's going to be a binomial process because the outcome in any trial is actually going to be, uh, characterized by, it's going to be dichotomous in nature. Okay, it's either I record, I see success, or I mean the head or tail. It's either head shows up or tail shows up. Okay, and that's what I call, that's gonna by dichotomous in nature. It's gonna be binary. Okay, and because of that, for my data, of course, I'm actually gonna use binomial distribution. But you know what? For the prior, okay, before going into before performing the experiment, of course, like I said, before collecting data at all, of course, what is a probabilistic description of the state of nature before data is being collected? Before data is being collected, of course, that can be thought of to be a beta distribution of the first kind. So we are the prior distribution I'm actually going to be using right now is going to be the beta distribution of the first kind. Okay, so if we're using a beta distribution of the first kind as a prior density, okay, uh, how can we have what is the values of the parameters, because the different values of the parameters, the parameters in the beta distribution of the first kind are alpha and beta that I wrote on the on my screen right now. And you know what? When the values of alpha is the same thing as beta, okay, the alpha and beta here are the shape parameters, okay? They are the shape parameter because when you try to vary alpha and beta, you're going to have a different shape. And that is the reason why the beta distribution of the first kind is actually flexible. Okay, it's flexible because of the fact that, you got two shape parameters in that. Now, whether the beta distribution of the first kind, whether it's going to be a weak prior or not, that actually depends on the values of shape parameters, alpha and beta. Okay. Now, take a look at what I'm showing on the screen right now. If take a look at that, is the alpha equal to 1, beta equal to 1? If alpha is 0.5, beta is 0.5, it's alpha and beta, the shape parameters are, if they have the same value, of course, I'm actually going to have what we call a weak prior. Okay, but you know what, it's not as if a weak prior is bad. Okay, it's not bad. Okay, in some situation, of course, it could work so great, but you know what, alpha and beta cannot be equal to 0, because when I was specifying the distribution the other time, I said, alpha must be greater than 0, beta must be greater than 0. But when you take a look at this guy here, where I got a beta into 0, 0, of course, that is going to be regarded as an improper prior. Okay, it's going to be an improper prior. Okay, if you take a look at alpha equal to 1, beta equal to 1, alpha equal to 2, beta equal to 2, and so on like that, that's not going to be improper. Okay, but in a situation where you have 0, alpha equal to 0, beta equal to 0, of course, it's actually going to be an improper prior. Okay, and that is not going to be fine at all if we use that, to if you combine that with the likelihood data. Okay. Now, the next thing that I actually want to talk about, I've walked you through what we mean, the week prior. Okay, when you are trying to look at, the using the beta distribution of the first kind as your prior density, and what the parameters, the shape parameters, the alpha and beta, what they can be. Okay, they can be equal to 0 the moment they are 0, 0. Of course, you're actually going to have what I call improper prior. Okay, and of course I can actually demonstrate that with you right now. I'm actually going to stop my share right now. Then I'm going to share my whiteboard. Give me 1 second. I'm actually going to share my whiteboard. Okay, so I'm going to share my whiteboard right now. If you take a look at my whiteboard, like I said, when X follows a beta distribution of the first kind with parameter alpha and beta, of course, the f of x is actually going to be equal to x raised to the power alpha minus 1 or 1 minus x raised to the power beta minus 1 divided by b of alpha beta. And don't forget I said alpha has to be greater than 0, beta has to be greater than 0, and of course x, which is the random variable, must lie between 0 and 1. Okay, so if that is what I have, if I want to test, okay, if alpha equal to 0, beta equal to 0, what am I actually going to get? Okay, if I plug in that into the distribution right now, I'm actually going to have x raised to the power minus 1 and 1 minus x raised to the power minus 1. Then I'm actually going to have b of 0, 0. Now, when you take a look at what I have here, this is improper. Okay, it's that is not going to integrate. If I use a range of 0 to 1, okay, that is not going to be a valid PDF. Okay, that is not going to be a valid PDF at all. Okay, if you try to integrate that over the range of 0 to 1, of course, the total area under a curve is not going to be equal to 1, and therefore that particular weak prior is actually going to be an improper prior. It is not all weak prior that are improper prior. Okay, I'm just giving you an example of, what of that that can be, improper prior. Okay, take a look at that right now. So this is not going to make sense. Okay, so I'm going to go back to the lecture material right now. Okay, so give me 1 second. I'm actually going to go back to the lecture material right now. Now, the next thing we want to talk about now is what we call conjugate prior. Okay, we actually want to talk about, and what do we mean by conjugate prior? Of course, when the if the prior, if you take a look, when the prior and the posterior, okay, if they are actually from the same distribution, okay, if the prior like that, and that's why I said, if I have, for instance, I have a beta prior, okay, and of course the posterior, if it is also beta something, okay, so which means we can only be talking about a conjugate prior if and only if the prior and the posterior, they are in the same class of distribution. Okay, so if the prior and the posterior, irrespective of the nature of the likelihood, okay, irrespective of the nature of the likelihood, okay, so if the prior density and the posterior, they belong to the same class of distribution, of course, we're actually going to have what we call a conjugate prior. And let me tell you this, what you can use as prior that will be conjugate, we have to be from a family of exponential, or we have to come from exponential family of distribution. Okay, before now, I think I've walked you through what does it what it takes a density function, or what it takes a probability function to come from an exponential family of distribution. And that is the reason why, members of exponential family of distribution are mostly being used as a conjugate priors. Okay, and I'm actually going to give you an example of one. So if you take a look at what I'm trying to showcase right now, so in the beta distribution is a conjugate prior for binomial likelihood. Why? Why is it a conjugate prior for binomial likelihood? I said something the other time. If I'm performing an experiment, a binomial experiment, okay, an experiment that is actually characterized probably with two possible outcome that is dichotomous in nature, the one I call binary, of course. And of course, I said the probability distribution for that experiment is actually going to be binomial distribution. Okay, the binomial distribution is actually going to be likelihood, and of course, uh, the prior that can be conjugate to binomial distribution is actually going to be beta distribution of the first kind. Okay, don't forget that I said the other time the beta distribution of the first kind, the random variable, is in the range of 0 to 1. Okay, therefore, if I combine the beta distribution of the first kind with the binomial distribution as a likelihood, what I'm going to have at the end of the day is going to be called beta binomial distribution. And of course, the beta binomial distribution is a family, or it's more, it belongs to the same family of distribution with a beta distribution. Okay, which is continuous in nature. Okay, so I'm actually going to show you, an example of that. So another example is when you talk about Poisson and gamma. Okay, the gamma distribution, is a conjugate prior for Poisson distribution. Okay, and I'm actually going to walk you the mathematics of that. Okay, so we want to have an illustrative example right now, just like what I said. Okay, on beta 44. Suppose you have a beta 44 prior distribution on the probability theta that a coin will yield a head when spun in a specified manner, and the coin is independently spun 10 times and head appear fewer than 3 times. You are not told how many heads were seen, only that the number is less than 3. Okay, so calculate your exact posterior density up to a proportionality constant, okay, for theta and sketch it. Okay, so I'm actually going to show you something right now. What I'm showing on the screen right now is the beta distribution of the first kind. Okay, this is more or less like a prior. Okay, this is a prior distribution. And let me tell you, what I specified the other time, the beta distribution I specified the other time was specified around random variable x. But in the real, a Bayesian framework, what we do, of course, the prior distribution is actually going to be the probability of the state of nature before we collect data at all. There's not going to be a random variable x. Okay, so the theta, the parameter is going to vary. Okay, the parameter is more or less like a random variable in that situation. Okay, so and that is the reason why you take a look at this guy here, or the parameter theta is a random variable. Okay, and of course this the parameters, let me just tell you this. Okay, as we're looking at this right now, we got 2 parameters, the alpha and beta, which are the shape parameters. Okay, but theta here is acting like a random variable because in the Bayesian framework, okay, we take a parameter theta as a random variable. Okay, so the distribution that I have right now, that I'm specifying right now, is a beta distribution of the first kind, and this beta distribution is actually a prior probability distribution of the parameter of unknown parameter theta, and this parameter theta right here, we believe it lies between 0 and 1. Okay, and that's exactly what I circle right now. Okay, so that is a prior. Okay, and if you take a look at the shape you're seeing right now, okay, take a look at this code, right? You can actually run that in out. For you, if you actually want to see the shape of your prior density, because it is available. You see the shape of your prior density at different values of parameter theta. I said something here. The parameter theta lie between 0 and 1. So if it's lie between 0 and 1, then I can inclusive, I can actually consider 0, 0.1, 0.2, 0, so on like that up to 1. And that's exactly what I have right here. Okay, so you can actually plot. Okay, so what you are seeing right now, okay, if you follow the code here in now, okay, of course, you can actually have a view of the shape of that density. I'm talking about the prior density, okay, and that is what I'm actually showing you right now. And of course, in showing you this, of course, I'm assuming that alpha equal to 4 and beta equal to 4. Okay, I'm assuming alpha equal to 4, beta equal to 4, and that is what I specify right here. Okay, so what I have right here now, of course, will enable you to view the the probability density function of your your prior, okay, the way it's actually going to look like. Okay, so the next thing I actually want to do, I want to go back to the question now. The question said, suppose you have a beta 4 4, alpha equal to 4, beta equal to 4, or prior distribution on the probability theta that a coin will yield a head when spun in a specified manner. Okay, the coin is independently spun 10 times. Okay, and heads appear fewer than 3 times. Okay, so if that's really occur, then what do they want you to find? They want you to calculate your exact posterior density. Okay, so how can we uh, calculate the posterior density? Of course, if you want to calculate posterior density, uh, what we want to do, the posterior density is actually going to be f of theta given x. Okay, and that is going to be proportional, okay, to the likelihood. Okay, the likelihood is actually going to be f of x given theta, okay, from I start from 1, we're talking about the joint likelihood, then multiply by the prior probability. Okay, so this is actually what we're looking for. Okay, and we believe that the posterior density is actually proportional to the likelihood, to the product of the likelihood and the prior density. Okay, and that's exactly what we're actually going to use. Now, if you take a look at what I have right here, that is going to be, we actually need to know the form of the probability distribution for the data. Okay. Now, of course, if I'm talking about a coin, okay, tossing a coin, I could have a head, I could have a tail. Of course, that's going to be a binomial process. And of course, we're going to use a binomial distribution for the likelihood. And of course, we're using a beta distribution for the prior. Okay, and of course, if I combine the prior with with a likelihood, of course, I'm actually going to have a posterior. Now, I'm actually going to walk you through that right away. Now, take a look at that. The posterior is the probability of theta given data, which is proportional to the prior, okay, multiplied by the likelihood. Of course, the likelihood is the probability of data given theta. Okay, you can see that now. Okay, so we have been able to specify our prior probability to be this guy. Okay, that's our prior probability. Okay, and don't forget the shape parameters have been given to be 4 and 4. Alpha equal to 4, beta equal to 4. Okay, now the next thing that I'm going to write based on that, if I make use of this guy here and I plug in, alpha equal to 4, beta equal to 4, I'm actually going to arrive at this. Take a look at that. Now, how do I arrive at that? Some of you may be wondering. I'm actually going to try that. I'm going to walk you through that now. Okay, let's plug in the value of alpha into that. Okay, P of, theta. If I want to do that, I'm actually going to write equal gamma, okay, 4 plus 4, divided by gamma 4, then theta raised to power 4 minus 1 is actually going to be 3, and 1 minus theta, give me 1 second. Give me 1 second. I'm actually going to rewrite that now. Okay, like I said, we alpha equal to 4, beta equal to 4. So I'm going to write the P of theta Okay, alpha equal to 4 or beta equal to 4. Okay, now the p of theta equal to, that is going to be gamma 4 plus 4 is going to be gamma 8 divided by gamma 4, then theta raised to power 3, 1 minus theta raised to power 3. Okay, now when you take a look at this guy here, that's a constant, right? So in such a way that if I want to rewrite this one, I'm actually going to write p of theta proportional. Okay, proportional. This is a proportional sign. Okay, theta raised to power 3, 1 minus theta raised to power 3. So that is how we got that one. Can you see now? Because this guy here is more or less like a constant. Okay, now our p of theta is proportional to that. Okay, now the next thing now is to talk about the likelihood. Okay, like I said, the likelihood is actually going to be binomial. Of course, the binomial this time around, the probability of the data, okay, given theta now, we actually going to have, you remember, n combination x, theta raised to power x, 1 minus theta raised to power n minus x. I think you remember that. And of course, we're given that the number of trial is 10. Okay, the number of trial is 10, and of course the number of success, they say, is fewer than 3. Of course, fewer than 3, we're going to be like less than 3. That's going to be 0, 1, 2. Okay, so I'm going to consider a situation where s equal to 0, where s equal to 1, and where s equal to 2. Okay, and don't forget, when I consider, don't forget I said my n equal to 10. That is the number of trials as suggested in this question. Okay, and of course fewer than 3 number of x. Okay, fewer than 3, of course, it's going to be 0, 1, 2. And that is why you're going to do 10 combination 0. That's why you're going to do this for when s equal to 0, for when s equal to 1, when s equal to 2 in the binomial framework. And at the end of the day, you're actually going to have that, okay, which is going to be a function of theta. Okay, so that is going to be the probability of data given theta, which is the likelihood. Okay, so that's going to be likelihood. So like I said, this guy here is our prior density, and this guy here is the likelihood. Okay, so that is a likelihood. Like I said, the binomial, we got a binomial likelihood, and we got a prior we got a the prior density, which is we're actually using the beta distribution of the first kind when alpha equal to 4 and beta equal to 4. Now this is what we have. The next thing is just to combine them to be able to have a posterior. Okay, now that is what we have now. Now, if we want to have a posterior, which is the probability of theta given data, so how do we get something like this? I'm actually going to show you right now. Okay, so you need to combine this guy with this guy right here. Okay, if you combine that, of course, that is what you're going to have. Because if you multiply theta raised to power 3 across board, of course, you're going to have theta raised to power 3 here, theta, and so on like that. Look at that. So multiply the direct multiplication of this with this. We actually give us what we have right here. Okay. Now take a look at that. If you multiply this guy by this guy, that is going to give you theta raised to power 3, then which is this guy here, and 1 minus theta raised to power 3 times 1 minus theta raised to power 10. When you look at the law of indices, that's going to be 1 minus theta raised to power 13. Okay, you're going to use this to multiply every other one there, and of course that will actually give you your posterior density. Okay, so this guy here is the posterior density that I talk about. This is the posterior. This guy here is a likelihood. Okay, that guy is a likelihood, and this guy here is a prior. Okay, now so you can see that right now. Okay, so the next thing that I'm actually going to talk about is, when I started the other time, I started by plotting the probability of theta against various values of parameter, I sketch the prior density. You saw the shape. Now, do you know that we can also have a posterior? We can also have a look at the shape of the posterior density. Now, what am I trying to talk about? I'm trying to talk about this guy here. Okay, this guy here is a function of theta, right? Now, and of course, we know the state space of theta, right? Which go from 0 to 1, right? Of course, we can actually plot that over the range of parameter theta. So, excuse me, if you want to do that, of course, you can actually, there's a code right here. You see that now? That is a code, okay? And if you want to start, like the first one here is actually for the prior density, the one for the prior density, and this guy here is for the posterior. Okay. Now, when I plot the prior density and I plot the posterior density, do they actually look alike? Okay, do they look alike? Then we're actually going to see. Now, this guy here is what I find out, using this particular code. If you write that code in R, of course, you're actually going to have access. You're going to see that picture, and this particular code actually lead to this. Okay, this is a posterior. Now, what did you observe in the shape of the prior density and the shape of the posterior? Don't forget the prior density. That is a probabilistic description of the state of nature. Okay, the data have not even been collected. Okay, but after collecting your data set, okay, after updating your prior knowledge, okay, because the data set will update your prior knowledge, and this is this kind of shape that you are having. Okay, now you can see that the shape are kind of different. Okay, you can see that now. Okay, so that is equal to actually to have the shape that I talk about. And don't forget that this is a posterior density that we derive the other time. Okay, okay. Uh, do you know that for better understanding, you can actually superimpose the two shapes on the same graph just for effective comparison? And of course, you're going to see that here they're going to have different center. Look at that. This is the center for that one. This is the center for that one. Okay, so this guy here, of course, I'm talking the one in red is posterior, and then the one in black is more or less like the prior. Okay, you can see that now. Okay, so this is just to tell you, of course, the likelihood. I'm sorry, the posterior mean is actually going to be different from the prior mean. Okay, based on what I'm seeing right now in this graph. Okay, so when you superimpose them, when you plot both the prior and the posterior on the same graph at the same time, and that will give you an opportunity to be able to compare them and say that they got a different posterior, they got a different mean, as you can see in what I'm showcasing right now. Okay, so I'm going to go into another example right now. And of course, in this example, the posterior distribution as a compromise between prior information and data. So let Y be the number of head in n spins of a coin, whose probability of head is theta. Okay, so if your prior probability for theta is uniform on the range of 0 to 1, derive your prior predictive distribution for Y. Now, let me tell you something. When we talk about uniform, of course, uniform distribution is a special form of a beta distribution. Okay, the other time, when you have a P of theta, the P of theta is if theta equal to, you have 1 minus theta raised to power beta minus 1, and divided by B of alpha beta. If alpha equal to 1 and beta equal to 1, then you got a uniform distribution. I'm going to say that again. If alpha equal to 1, beta equal to 1, then you're actually going to have a uniform distribution. If I plug in 1, of course, my P of theta right here is actually going to be equal to 1. Okay, when I plug in 1 right here, when alpha equal to 1, beta equal to 1, the B of 1, 1 is 1 because gamma 1, gamma 1 divided by gamma 2 is actually going to be 1. Okay, and that is the reason why uniform distribution is a special form of a beta distribution. And of course, when a beta distribution, with the parameters alpha and beta equal to 1, then that will lead to uniform distribution. Okay, so what you want to find, we want to derive the predictive distribution for y. Not only that, uh, we also want to solve another problem that asks, suppose you assign a beta of alpha beta prior distribution for theta, and then you observe y x out of n spins. Show algebraically that your posterior mean of theta always lie between your prior mean and the observed relative frequency of n y over n. Okay, of course we actually want to show that now, but we're going to first show the first one. And the C part show that if the prior distribution on theta is uniform, the posterior variance of theta is always less than the prior variance. Okay, so we also want to show that. And uh, uh, the last one is actually give an example of a beta, alpha comma beta prior distribution and data y, and in which the posterior variance of theta is higher than the prior variance. Of course, you know what we said in C. We said that if the prior distribution on theta is uniform, okay, if it is uniform, the posterior variance of theta will always be less than the prior variance. Don't forget, we actually want to have an improvement on the prior variance, okay? And we believe that when the prior density is uniform, we can actually achieve that. But if you take a look at the D part, can we have an example? Can we have a way, can we have a situation whereby the posterior variance will be higher than the prior variance? Of course, I'm actually going to walk you through that. Now, let's start from number 1, okay? Trying to find the predictive. Now, like I said, if I want to find the predictive, distribution of y, okay, which is the probability of y equal to k, of course, I'm actually going to integrate, that probability of y equal to k given theta with respect to theta. Okay, now when you take a look at what I'm doing right now, some of you may be wondering, why is it going to be this guy here? And I'm actually going to tell you right now. Take a look at that. If I want to obtain the posterior, for instance, okay, if I want to obtain the posterior of theta given y, I'm actually going to do, uh, I'm actually going to do combining the likelihood of y given theta by the prior, right? Okay. Now, this guy here is a constant of proportionality. Okay, if I want to rewrite that, of course, I'm actually going to write equality. Okay, when I write equality, of course, I'm actually going to write, it's going to be pi y of that, the p of theta divided by, if I'm talking about continuous random variable, of course, it's actually going to be integral of that, y comma that, the p of theta, the theta. That's what I'm going to have. Okay, so when you take a look at this guy here, the denominator here is what we actually call the predictive. Okay, when we want to talk about the predictive distribution of y, that's exactly what we mean. Okay, and of course, situation which means we're focusing on this guy here. Okay, focusing on this guy here, don't forget the p of theta equal to 1 because we're talking about uniform. Okay, if we're talking about uniform, p of theta equal to 1, the only thing we're going to integrate is going to be likelihood. Okay, and that is the reason why when you take a look at what we're integrating right here, we are actually integrating the likelihood. Okay, because the uniform is actually, the prior distribution is a uniform, which is equal to 1. Okay, and that's why we're going to be integrating the likelihood with the range over the range of the parameter. And that's exactly what we have right here. Okay, so that is exactly what we're trying to do right here. Okay, so And that this is the explanation of that. And this guy here, of course, that is what we're trying to do. Okay, that's what I just explained right now. Okay, so like I said, the next thing we're actually going to do is, what is the likelihood? Of course, the likelihood is going to be binomial distribution. You know that? And of course, what is replacing that now is a binomial distribution when y equal to k. Okay, initially it's supposed to be n combination y, theta raised to power y, 1 minus theta raised to power n minus y. But we said y equal to k. So, and that is why we're having that. Okay, so the next thing now is just to integrate what I have right here. Okay, we're going to integrate that. Okay, so I'm actually going to show you how to do that now. At the end of the day, we're going to have 1 over n plus 1. But you know what? I'm actually going to walk you through this, how you can actually achieve that. I'm going to write it down, and I'm going to show you. Now, I need you to focus on this screen, as I'm going to show you how the predictive probability is 1 over n plus 1. Okay, so I'm actually going to write, this is n combination k, theta raised to power k, 1 minus theta raised to power n minus k, the theta. Okay, so I'm actually going to show you right now. Okay, give me 1 second. I'm going to stop my share. I'm going to, share my whiteboard. Okay, so like I said, I'm actually going to share my whiteboard right now. Okay, so what we actually want to do, we want to find an integral, integral from 0 to 1, n combination k, theta raised to power k, 1 minus theta raised to power n minus k, the theta. We want to show that is 1 is equal to 1 over n plus 1. We actually want to show that. Okay, now we want to integrate with respect to theta. And if we want to do that, of course, I'm actually going to bring n combination k outside. Then I'm actually going to have from 0 to 1 theta raised to power k, and 1 minus theta raised to power n minus k, the theta. Okay, now when you take a look at this guy here, we can actually use the beta function of the first kind. Okay, according to the beta function of the first kind. Okay, so according to the beta function of the first kind. Okay, now the beta function of the first kind, we have that b of alpha beta. B of alpha beta is actually going to be 0 to 1. Okay, and I'm actually going to have theta raised to power alpha minus 1 and 1 minus theta raised to power beta minus 1 d theta. Okay, that is according to the beta function of the first kind. Now, if that is going to be the case, we need to be able to determine our alpha. So which means I'm actually going to say alpha minus 1 equal to k, and beta minus 1 equal to n minus k. Okay, because I actually want to use a beta, I want to use this guy here on this. And if I want to do that, of course, I'm actually going to equate, okay, the exponent. Okay, so if I want to equate the exponent right now, I'm going to clean this guy here to have a space. Okay, and if I want to do that now, so what I'm actually going to do, I'm actually going to have alpha minus 1 equal to k. Then I'm actually going to have a beta minus 1 equal to n minus k. Okay, alpha minus 1 equal to k, beta minus. So that implies, right here, it implies alpha equal to k plus 1. Okay, it implies alpha equal to k plus 1, and this implies beta equal to n minus k plus 1. Take a look at that. That implies, so I've been able to obtain my beta, or alpha to be k plus 1 and beta to be n minus k plus 1. Now the next thing that I'm actually going to do now is to now rewrite this in this form. Okay, so if I want to rewrite that in that form, automatically what I'm actually going to have, this guy here will be written, if I want to write that. So I'm going to clear my board right now, for you to be able to see space, because I need a space right now. And of course, what I'm going to have next is going to be n combination k, then b, instead of alpha, I'm actually going to have k plus 1. And instead of beta, I'm actually going to have n minus k plus 1. That is what I'm going to have. Now, if I have that one now, if that is what I have right now, so the next thing that I'm actually going to do is, uh, since I have, this is what I have, n combination k into that, then I'm actually going to write a non-integral definition of a beta function. Okay. And when I say non-integral definition, I'm actually going to write that right now. Okay. So non-integral definition, non-integral definition of a beta, beta comma alpha beta, non-integral definition is actually going to be gamma alpha, gamma beta divided by gamma alpha plus beta. Okay. So I'm actually going to write this guy here in terms of the non-integral definition of a beta function. Like I said, it is gamma alpha, gamma beta divided by gamma alpha plus beta. Okay, so if that is what I have right now, I'm actually going to clean my board, and I'm going to write the next thing. Okay, so the next thing that I'm actually going to have right now is going to be, so n combination k, then I'm going to have gamma k plus 1. Okay, gamma k plus 1, gamma n minus k plus 1, divided by gamma. I'm actually going to add k plus 1 to n minus k plus 1. Of course, k is going to cancel minus k, and I'm actually going to have n plus 2. Now, that is what I have right now. So I'm going to clear my board. Now, so that is what I have. That is what I have right now. So if I have this one right now, so, and then I'm actually going to write, so if I have n combination k, now, an n combination k is n factorial divided by n minus k factorial. Then I'm also going to write gamma k plus 1, and then gamma n minus k plus 1 in terms of factorial. If I want to write that in terms of factorial, of course, gamma k plus 1 is actually going to be k factorial, and gamma n minus k is actually going to be n minus k factorial. Okay, I'm going to say that again, because in the law of in the law, so gamma k plus 1 is k is going to be k factorial, because you remember that 5 factorial is the same thing as let me see. Okay, don't let me go that way. Don't let me go that way. What I'm actually going to do next is this. If I take a look at that, what is gamma k? Okay, gamma k is k minus 1 factorial according to the law. Okay, gamma k means k minus 1 factorial. Okay, so which means gamma k plus 1 will be k factorial. Okay, it's just going to be subtracting 1. Okay, so I'm actually going to rewrite that right now. So gamma k plus 1 is actually going to be k factorial. Gamma n minus k plus 1 is actually going to be n minus k factorial. And then gamma n plus 2 is actually going to be n plus 1 factorial. Take a look at that. K factorial cancel k factorial. N minus k factorial cancel that. And what I have right now is just n factorial divided by n plus 1 factorial. Now, if I have n plus 1 factorial, is actually going to be, this n factorial divided by what is n plus 1 factorial. I can rewrite that as n plus 1 into n factorial according to the law. So n factorial cancel n factorial. Finally, I got 1 or divided by n plus 1. So which is the predictive probability of y that we are asked to show. Okay, I think you guys can see that now. Can see that right now. So we have been able to prove that. Okay, for those of you who have a trouble time understanding that, of course, you can actually meet with me during my office hour. Okay. Now I'm going to stop my share right now, and I'm actually going to go into the lecture material. Give me 1 second.